Recording. Okay. So the test for this class is on Wednesday, May 12th at 4 o'clock. It's really just a third test. And so that will cover units 9, 10, 11, and 12. And 12 just has a single lab, a single circuit for you to build. And I think I've posted everything except the Zoom sessions of me demoing things and answering questions. So it's unit 9, which is flip-flops and counting, and something on hardware generations and transistors and logic gates made out of transistors and sometimes diodes. And 10 is combining a capacitor and a transistor to make DRAM, the digital comparator circuit. So you're comparing sort of one 4-bit word to another 4-bit word and deciding if the words are equal, or if the first word is greater than the second word, if those words are unsigned integers, if they're positive numbers. And then we started talking about putting all the sort of pieces we had together, making an architecture, and mapping out a command, a fairly simple command, but at this very lowest level, that simple command gets complicated. And sort of what are all the little sort of micro steps or micro instructions or micro code to do even the simplest thing in an architecture. And then this week we'll do unit 11, which will have inductors. There's 2 more circuits for us to sort of get through. A circuit where there's this new element, an inductor with a resistor, and then one when there's an inductor with a capacitor. And we'll study the behavior of those and play around a little bit with stacks. And part of the lab will be to sort of map out the instructions of something with the stack. Oh, I have a chat. Can you show the DRAM part of lab 10? Okay, I think I built that. Yeah, DRAM lab 10 part A. Let me just make sure we're talking about the same thing. You're talking about the DRAM as opposed to this. So the DRAM, okay, was this circuit, which had 2 inputs, 2 resistors, a transistor, and a capacitor. And what was asked for in the lab? Build a DRAM, shown in the lecture, so I'm showing it now. It's also on the YouTube video lecture. Set the circuit so that the output is high, and then place the circuit in the hold state. Describe what happens and its significance. Okay. So in this circuit, E determines whether or not you are writing. And so I will make first E high so I can write, and then I want to write a 1, so then I'll make D high. And then that will be a set. So if E is high, I'm either setting or resetting. And then D determines if it's high, it's setting. If it's a low, it's resetting. So I'm going to set E high, so I'm writing, and then D high, so I'm setting. specifically setting. And then I'm going to hit E low, and that's going to put me in the hold state. And then I want to see what happens while I'm in the hold state. So I'm going to turn it on. I'm going to flip E. So now I'm writing. And then I specifically want to write a 1. I want to set. So now the voltage has gone up in 4.4 something. So that's a high. Our reference is a 5. So 4.4 is pretty high. And now I'm going to flip the E switch and put it into the hold state. So now I'm in the hold state. I'm holding a 1. It doesn't matter what D is. What matters is that D was high when I was last enabled. So last thing I wrote was a 1, and now I'm in the hold state. And we can see in the hold state that voltage sort of slowly changing. It's changing, but that's relatively slow, and in computer times, that's a slow change, but it is changing. And that is the significance of that, is that the resistance is not infinite of this transistor in the off state. There's the resistance of the transistor in the off state, and then there are other things that are attached. Say, for instance, here, this voltmeter has a resistance. And so these things that, so there's some high resistance stuff that's not infinite resistance. So there's still a time constant. There's still a changing voltage. In this case, this capacitor is discharging, and we would say that it is leaking. It's supposed to be holding its charge, but that it's not quite holding its charge. It's leaking some of the charge. And then the significance of that is that we know that DRAM requires refreshing, that it's doesn't always do a good job at holding its voltage, and therefore it occasionally needs refreshing. That's the significance of the changing, is the requirement for refreshing of DRAM. Okay. So that is, so 10 was making things from NANDs. We made a bunch of stuff. We talked about last week about making a bunch of stuff of NORs. It's very similar, but not exactly the same, but very similar. And then that we just talked about DRAM. We showed a digital comparator. The one thing to note about a comparator is, the question of what's in the box. That I show an example of what a comparator looks like, but you have to know that this box is a subcircuit and that there's stuff in there. And if you don't like subcircuits and you just want to explicitly put 4 copies of what's in the box, that's allowed. But you just can't make an empty box with nothing in it and have a comparator. Okay. And then there was this simple architecture, and I did one of the instructions for you. I mapped out one instruction, and we emphasized that half of the instruction is what's known as the fetch, and the other half is the execute, and the fetch is always the same. And then there was one more instruction for you to map out, for you to have a go at, and then ask me questions about. So I will pause and see if there are any questions, and then if not, I'll start talking about inductor circuits. I think I will start talking about inductor circuits. Slightly longer pause. Okay. So our last circuit element is what's known as an inductor. Okay. So this involves a little bit about magnetism And I'll just dive right into the circuits, and you can work through this PowerPoint. I put in here somebody's demo. I copied somebody's demo from YouTube, so I couldn't save it to YouTube because I think I have my email open. That's why I keep dinging. Close that. Okay. I have in here, I made this PowerPoint in the time, at least the latest version of this PowerPoint sometime in the time of COVID in the fall, and I didn't have access, then I could do my own demo, so I had somebody else's demo, which was on YouTube, and I can't save on YouTube somebody else's demo, so I put this up just as a PowerPoint. But mostly my PowerPoints are too large. If I did all PowerPoints, IT would yell at me for taking up too much space. But this is the one that I've saved to do this way, and the rest I did by YouTube. So I will let you go through that and ask me questions about sort of how do we get to this thing called an inductor. And then let me just tell you, there is this thing called an inductor. And what it does is, as a circuit element, is it doesn't like you to change the current. So that is its function or its behavior in a circuit is it makes the change of a current a difficult thing to do. It doesn't stop it, but it just makes it harder to change the current. It sort of, it opposes a change in the current. Okay, so there's some blah, blah, blah here to tell you what an inductor is and what it has to do with magnetic fields. And then we get into the point where it is in a circuit. Okay, so let's get down to, and I'll see on Wednesday and then next week how things are going. But let me focus now on the things that might appear on the test so that you do well on the test, and then we'll explain extra things as we have time. Okay. So I want to close the DRAM, close the comparator. That's the comparator subcircuit. This is an LC. I'll want that later, but I want to open up an LR first. Sometimes I call it RL, sometimes I call it LR, but it's a circuit with a resistor and inductor. So the R is for resistor and the L is for the inductor. Open, I want to open. I'm calling it RL this time. Okay. All right, so here is this thing. That thing is supposed to be sort of coiling around, because that's how you make an inductor. You coil some wire. In fact, if you were a car person, an inductor, sometimes known as a coil because that's its shape, and sometimes known as a choke. Don't ask me anything about cars, I don't know. But that sort of bumpy shape there that multisim is giving you is supposed to represent a coil of wire. Okay, so we have this inductor. It comes in a unit called Henry, and this is a pretty big inductor, and it's millihenries. And then I have a resistor. Okay. And then I have a switch and a battery. I'm going to take out the inductor for a second. I didn't want to do that. I just moved its label. I wanted to move the whole inductor. Okay, let's have this circuit without an inductor. Open up the oscilloscope. Some of my pictures will have a 2-channel, but that doesn't exist anymore. We need it's the 4-channel, and that's over here for 4-channel. There's another oscilloscope before the 4-channel. I don't like that one. If you ask me, if you build a circuit with it and you ask me a question, I'm going to make you change to the 4 circuit, the 4-channel one. I just don't like the other one. I'm prejudiced against it. I don't know, but I don't like it. Don't use it if you're going to talk to me about it. Okay, so let's see what this circuit does. I'm going to turn it on. I'm going to click in the space. I'm going to flip the space bar up and the space bar down and turn it off. Okay. And here's what we had. It was a low, and then it goes up almost instantly. And then it goes down. And I played here with the time constant. So remember, I can make the time division smaller or I can make them bigger. If I make the time divisions bigger, then this little separation between it going up and going down gets closer. If I have a big time division, it gets more stretched out. That's just the way I'm looking at it, not what it is, but the way I'm looking at it. What time scale am I looking at it on? Okay, now what I want to do is bring the inductor back in to see its effect. And remember what I said, the inductor does. The inductor doesn't like change in current. Where did the current change? Here, when I flipped the switch. There was no current, and then there was current. That's a big change, an infinite change in current. This is disjointed. If I say, what's the change? It's like a rate of change. It's like, the current didn't change by that much, but it changed, but the rate of the change was infinite because it took no time to do it. If I said, what's the change in current will be delta I, the change in current over delta T, the change in time, but the change in time, there's almost no time here. It just went straight up. And so that rate of change of inductance of current, the rate of change of current is very high, is infinite right here. And that's what the inductor doesn't like. So that's what's going to change when we bring in the inductor. All right, so I'm going to do the same thing. I brought the inductor in now. I'm going to turn it on, click in the space, flip the switch up, flip the switch down, and turn it off. Okay, now we see this and that. So it doesn't go straight up like it did before. It does this curving. And we've seen this form before. This shape should be familiar to you. This is the shape that we saw in RC circuits. And there is a little bit of a corner here, and then it goes up to some saturation. Okay. So I want to change the time constant. I want to stretch this out a little bit because that's the behavior I'm interested in. So I want it spread out a little bit. So I want a smaller time constant, which will stretch it out a little bit. That's probably stretched out enough. I don't like to go up too fast. I want to see a little bit of a spread here. And then you remember this game. If you don't remember this game, you better learn it fast. We want to go up to 63%. So first guy with this needle, I call number one, or the number one needle, I want it to be at this corner. So we see down here right now, I'm at 5 picovolts. Pico, that's very small. I'm looking for it to change, and then I'm going to go back. It just changed to 140 millivolts. I'm going to go back. So that's the last time it was very small. I'll effectively call it 0. Okay. And then I'm going to go up to, it's the same math as it was before, 63% of 5. I'm going up to 5. You can see that this is 5 volts or 4.998. We're going to call it 5. And I want to go up to 63%. One-time constant is 63%. So 63% of 5. Again, we played this game before. 0.63 times 5 is 3.15. So I want this voltage to be 3.15. It's 379. I'm looking for 315. And then I find the one that is closest, 313. Okay, I'll figure that's pretty close. And then here's my time constant down here, 397.9 microseconds. US, which really should be a mu-s, which is microseconds. Okay, so that is the theoretical time for the change. This is I'm measuring the voltage over the resistance. And so this is it's the current that's changing. And before the current sort of changed instantaneously, now that change is spread out over some time. This time constant is not the time for it to completely take place. Strictly speaking, it's an infinite number of them to completely take place. But you can get, if you do, I don't know, 3 of them, it's like 99%. But what we call the time constant is 63%. Okay, it's related to the number E. Okay. So there we have the time constant, and it is supposed to be theoretically L over R. So that is our simulation measurement of the time constant for when the current is increasing. And it's supposed to be L over R. So let's see what L over R should be. 470 divided by R, 1.18. And I get 398. So that seems to be consistent. And then what about my unit? I have millihenries, MH, millihenry divided by kiloohm. So a henry divided by an ohm is a second. And then milli is 10 to the minus 3. Kilo is 10 to the 3, but that one's in the denominator. So I have 10 to the minus 3 divided by 10 to the 3, which is 10 to the minus 6. I'm dividing something small by something big, so I'm getting something very small. And so that unit, millihenries divided by kiloohms, is going to give me microseconds. And there's the unit there, microsecond. So that works out well. The simulation was 398. Doesn't always work out that well. This might be, this might come out to be 410 or something like that. We'd still take it, or it might be 380 and we'd still take it. So it's not always this clean, 398 and rounded here 398. That's a little better than we usually expect, but it ought to be pretty good. And you can also do the going down. La 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 la. It's taking me too long. Oops, there it is. Okay. And our usual going down game is, okay, here it is 5, and I want to see the last time it's 5, and then go back, there it's 5. And then when you're going down, it's 37%. So 0.37 times 5 is 1.85. So that's what I want the 2 to be at, 1.85. 1.856, that sounds pretty good. So there it is. And this time going down, I'm getting 415. So it's not quite as nice as it was going up, but still, in the ballpark. It's, 398 or about 400, 415. Okay, that's close enough for us in these simulation things. What if I were mean? I'm sometimes been known to be mean. If I were mean, what would I do? What would I do if I were mean? Okay. I would have another resistor. I don't know, 243. And I don't know. I could put it in parallel. And then let's play the game. Simulation. Turn it on, click in the space, flip the switch up, flip the switch down, turn off the simulation. Okay. So let's work on the going up. Okay, so it was find the corner. And we were going up, it was 315, right? 0.63 times 5 is 315. Okay. So here I'm getting a 605 microseconds. Now, what would it be? Oh, I would take the L divided by the effective R, or the, so that I have to add these two R's in parallel, the equivalent resistance. So I would do 2.43 1 on plus 1.18 1 on equals 1 on 0.794. Okay. And then it's L divided by that. So 0.794, and then it's 470 divided by 0.794. Is that what I said? Somebody tell me if I was wrong. And I'm getting 591.9 for the new time constant. And the simulation was 605. So still good, same ballpark. Questions? I'm trying to get you through test 3. There's going to be an LR circuit or an RL circuit. I'm dyslexic. I don't even know which one is right, the sort of common way to talk about it. But there will be a circuit with a resistor and an inductor. Okay, and we know how to deal with resistors in series and parallel. So I'm not going to talk about inductors in series and parallel, so you don't have to worry about that. But I might do something with resistors if I'm wanting to do a little bit extra, some kind of reviewy kind of thing. Any questions on RL? All right. Now I want to switch over to LC. This really has a resistor and an inductor and a capacitor. But when the switch is open, it's the resistor and the capacitor are the circuit. And so it's just an RC circuit. We know what that looks like. And when the switch is closed, it's an L and a C. So the resistor is with the capacitor and the inductor is with the capacitor, but they're never all three are in the circuit at once. So what's going to happen is when first it's going to be flat, and then I'm going to flip the switch and it's going to be a charging capacitor. We know what that looks like. That's that sort of hump going up and saturating. And then we're going to close the switch and it's going to do what you see here, this sort of oscillating effect. Okay, let's see it. All right. I'm going to click on the switch. I'm going to click in the space. I'm going to hit the space bar and the space bar and then stop the simulation. Okay. So there's the oscillating part. Here is this is the flat part. That's before I hit the switch. There's the charging capacitor part that we know and love. And then here's the oscillating part that we will soon grow to love. Okay. And so it goes, the charge across these two things, they're in parallel, so they have the same voltage, and so the voltage across either one of them oscillates. And when something repeats like that, a thing that we're often interested in is the time to repeat. So here's one cycle. It's up, it's down, it's back up. That's a cycle. And you can measure the cycle from up to up, or from down to down, or from going through zero and going down to going through zero and going down. If you go from zero going down to zero going up, that's only half a cycle. But if you go up highest to highest, max to max, or min to min, or zero going down to zero going down, those are all different versions of the period. Those are all supposed to be the same. So I'm going from 1 to 2, from a max to the next max, and that is taking me 5.882 milliseconds. So that's what the measurement looks like. Let's show you what happens. So I made this 300 millihenries. Let me make that much smaller. Let's replace it with another, a much smaller, let's say 15 millihenries. So now, again, start the simulation, click in the space bar, and then stop. Okay. And so now we can see it's much more bunched together. And if we want, then we can play with the time constant and stretch it out or bunch it up. And let me go all the way down to like 1 Henry, 1 millihenry, and turn it on. And so then what can happen if there's a small number of henries is it all just sort of bunches all together. So I had a flat, I had the charging capacitor, and then I had this just all bunched together. And if you see that, then you've got to play your time constant game and get it stretched out. and you still play the same game. You go from a high to the next high. So I'm high again, and that was 328.720 microseconds is the period. The period is the number of seconds for one cycle. So it is a seconds per cycle. A frequency is a number of cycles per second. And so to go from a period to a frequency, you take the reciprocal. So let me bring up a Word document, just a blank thing, play my weird snippy game. Okay, so T is the period, and that's the number of seconds per cycle. The frequency is the number of cycles per second. And hopefully by emphasizing the unit, seconds per cycle and cycles per second, you can see that they have a reciprocal relationship, that T is 1 on F, or F is 1 on T. That's the same equation, just rewritten. And so then I have a period of, move this over. No, I want this. So I have a period of 320, I'll say 329 microseconds. And so then I ask, what's the frequency? And so it's 1 divided by 329, and I'll put down here microseconds for now. So the number 1 over 329, I do the calculator. And 329, 1 on is 0.00304, I'll say. And then the reciprocal of microseconds, the reciprocal of a second is known as a hertz. But I don't have a second, I have a microsecond in the denominator. So I have something 10 to the thousandth, not thousandth, million, 10 to the minus 6 in the denominator. So I have 10 to the 6 in the numerator. If I divide by something small, I get something very big. And so I have megahertz. And that I could move the decimal 3 places, and that would change. I'm making the number bigger, so I'd make the unit smaller. So that's also 3.04 kilohertz. Or if I move the decimal place 3 more times, 3040 hertz. Okay. So what do you get when you run the simulation? You measure a period. But I'm not going to just ask you for the measured period. I'm going to ask you to figure out the corresponding frequency. So you're going to have to do this 1 on thing. It's an easy calculation, but the units sometimes take a little thinking. And then we need the theory. What's the theoretical frequency? Because I'm going to give you a formula for the theoretical frequency. And I'm going to show you in the Word document where it is. I'm also just now I'm going to demo for you how to get it from Excel, how to set up an Excel spreadsheet that will do the calculation for you. If you want to use a calculator, if you love math, then you just want to use your handy dandy calculator, fine. If you don't like this formula and don't like calculators, then put it into an Excel spreadsheet. And all you're going to have to do is change the L and change the C, and the calculation in Excel will update. So let me find that should be 11A, I believe. Let me down. Okay, so here we're talking about 11A. There's that LR circuit that we talked about. Here's the, and I ask you here to change the resistance. If I ask you to change the resistance, you don't change it. It's not 1.1, 1.2, 1.3. If I ask you to change the resistance, you make it, 1, 2, 3, or 1 and 2.2 and 3.3, or even bigger changes. But don't give me a little 10% change. I'm asking you how it depends on resistance. And if you only change a little bit, then you're setting yourself up for problems with noise, that you might get a slightly different answer. Something's supposed to be a little bit bigger, but it ended up to be a little bit smaller or something like that. And also, everything looks linear when the change is small. So if you only give yourself a small change, you're going to have noise. And even if you don't have much noise, it's going to look linear. And the dependence on the resistance is not linear. So, when somebody asks you to vary something, you give a reasonably decent amount of change. So it shouldn't be 1.1, 1.2, 1.3. That's not enough of a change to see what's going on. Okay. And now here we're doing the LC, and here's the formula: 1 on the square root of 2 pi times the square root of LC. So 1 over 2 pi square root of LC. And that's the theoretical frequency. If you want the theoretical period, you just turn that upside down. It'd be 2 pi, but that's not what I'm going to ask you. I'm going to ask you the frequency. And let me show you. Here I show you the Excel. Here's my picture, my screen cap of the Excel. And now I'm going to demo it for you, set it up. Okay, so I want Excel. I'm going to label a spot L for the inductor, a C for the capacitance, and then I'm going to call this freq for the frequency. And then let's see what we had in our simulation. Now we want to convert. So let me say that this is L in henries. And this is the capacitance in farads. And then I'm going to get the frequency in hertz. So I'm going to put everything in its simplified units, no millis or kilos or anything like that. Okay, now where were we? We were here and then here. So this last one that we just did was a millihenry. So that's 1,000th of a henry, 0.001. Our capacitance is a microfarad. That's 6. This was 3 places. This is 6. So 0.6 1, 2, 3, 4, 5 zeros, and then 2, 7. Okay, so that is micro. You could also say 2.7 E, that's how computers do scientific notation. It's times 10 to the minus 6, minus 6. And that's the same. So you can, this is just us doing the conversion. This is us using Excel scientific notation, either way. I could have done that here. 1 EE minus 3 per milli. Okay. Now here's the formula. So this is just two different ways. Rows 2 and 3 are just two different ways of doing the same thing. You don't have to do it both ways. You only have to do it one. But what was the formula? It was equal 1 over a whole bunch of stuff. So here's my parentheses for a whole bunch of stuff. And now I want to go in there and do that whole bunch of stuff. And then there was 2 times pi. So I'm going to say 2 asterisk pi. I'm going to do it the fancy way, and then I'm going to do it the silly way. So the fancy way in Excel to get pi is PI open close parenthesis. And then I'm going to multiply that by a square root or something. If that freaks you out, it doesn't freak me out, but if it freaks you out, pi is 3.14. Good enough for me. Okay. I'm going to go back to my PI open close, but again, if that's freaking you out, giving you errors, pi is 3.1415. I don't know. 14 is probably good enough for me. And then there was the square root. So Excel has a function, sqrt, the squirt function. And then it was L times C. So here's my L, and here's my C. And I'm getting that the frequency is 3062. And that was my, this was my megahertz result. And down here was my, just converted into hertz results, 3040 I got. And here I'm getting 3060. So that's fair enough comparison. We're happy with that. I'm going to copy this down just to that other row. I should get the same answer because these were the same numbers, just input a different way. But if you do this, if you work out the Excel rather than your calculator, 2 advantages. One, I'm asking you to change the capacitance. So if you have different capacitors, you just copy your formula down in Excel. Then I have you change the inductance. If you use the calculator, okay, you probably know some calculator tricks. I don't know. I'd have to put it in over and over again. Okay, but that is the game. This is how to do it in Excel. You can have your Excel spreadsheet ready to go, bring it to the test. That is the Wednesday of finals week. And just plug in the L and the C that I give you. Questions? Again, calculator's just fine, Excel's fine, whatever gets you through the night or the afternoon is just fine. Just so the Excel is an alternative for people who don't like calculators. Probably some crazy ass calculator on the internet that does LC circuits. Who the hell knows? Probably everything's on the internet. All right. What else? So that is down here. This stuff is sort of googly stuff. What's a low pass filter? What's a high pass filter? What's a tuner? What's resonance? What's a tuner? Okay. So that is 11A. And those circuits are both almost certainly on test 3. Those of you who did well on the RC circuit, well, then the RL circuit is just the slightest modification. Those of you who didn't learn it, they get one more shot. So this is 11B is some stack vocabulary, again, to Google some stuff. And then the second part is one of these mapping out instructions. So we're going back to, here is me explaining how the instruction works, and then you trying to fill in this table. So you'll note that I start at 4. My explanation, I'm at the top of page 2, and I'm starting with instruction 4. I'm all the way down at the bottom, down here. Here I'm starting at a 4. I start at 4 because the first 3 steps are the fetch, and they're always the same. So you find out what I did for on the slideshow. Sorry, no, in the Zoom, I did it for you. I wrote out exactly what I wanted for steps for the load the accumulator A. The first 3 steps are the fetch, and those are always the same. So you're always going to get the first 3 steps right. And then here I'm telling you what I want you to do for steps 4 through 4, 5, 6, 7. And there are 2 things. This is about using a stack and going to a subroutine. And there's going to the subroutine and there's coming back. And in the picture, I added a new box because I needed a stack pointer to have a stack. So the old picture is mostly the same, and then I added a new piece called the stack pointer down here. So that is that mapping out of those states. So we'll see if anybody asks me about that, say on Wednesday. And let's have a peek at 11B. So then I can say I've shown you everything. And then 11C is there's a RAM circuit. And I give you, I believe I give you, here's my RAM circuit. And since I'm on campus, I can just click on it. And here's this RAM circuit. These are flip-flops. If I put a bunch of flip-flops together, I have a register. I add here a decoder. And so if I have a bunch of registers and a decoder, that makes RAM. And so your job is to figure out how this circuit works. This is connected, these 1, 2, 3, 4 are probably, are they, no, 0, 1, 2, 3. These are connected to the inputs of the register. So this is the data you're trying to read in, because that's the D. Let me view, zoom in a little bit. Okay, maybe a little bit more. So these switches are connected to the Ds. So that's the data you're reading in. So this is going to be, if you try to write some data, this is going to be the data you write. The W is connected to the clocks. So that's going to be, remember that with these flip-flops, you have to go through a positive edge. So this W is going to control when you write. And over here, A and B, they go to the decoder. The decoder is our addressing system from way back in lab 4. So this determines where you're writing, which of the registers you write to. These determine the data that you're writing, and W determines sort of if and when you write. And so basically I give you this circuit, I ask you to operate it and get points for it on the lab, and then I give it to you again on the test 3 and say, operate it. And I will say, you know, write to location 2 a 6, and then show me that you're reading that 6 at location 2 that you just wrote. So you have to know how to get a 6 as the data. You have to know how to get a location 2. And these locations are numbered 0, 1, 2, 3. So you don't get your choice of who's 0, who's 1, who's 2, and who's 3. That's predetermined. You don't get to choose. It's chosen for you. So that is, you can add probes so you can see what's going on along the way. I recommend that. And I also recommend writing yourself good instructions in this lab so that on the day of the test, you can read those instructions if you're panicking and remember how the circuit works and operate it and get those points. Questions? If you don't ask me questions, I'm going to tell you why the LC oscillates. But if you have questions, I'd rather answer your questions than the ones I make up for myself. I don't see any questions. I've reviewed what you have to do. Oh, here's a question. Can you show how to put in a 6? Where do you want me to put in this 6? You can't just say in memory, you just can't say what you want to put in, but you have to say where you want to put it in. Half of memory is about the address. It's the value is at an address. So either he's got to type where he wants me to put the 6, or somebody else has got to shout out what location they want it in. There are 4 choices, 0, 1, 2, and 3. Are you yelling at me and I can't hear you, or? 0. In location 0, place a 6. Okay. So I am going to say location 0. So this controls 0. So that should be 0, 0. So A right now is connected high. I want it connected low. So now A is low and B is low. So that should be location 0. That should be this top register up here. And then he asked me for a 6. I'm going to pretend I don't know what a 6 is. I'll go over to programmer mode, decimal, put in, or let me go into hex mode. 6 is the same decimal or hex, but I might ask you to put in a C or something. Maybe I'll be mean that day. So put yourself in hex mode, and I want to put in a 6. Oh, that's 0, 1, 1, 0. So this is this should be low. So the 3 should be low. The 2 should be high. The 1 should be high, and the 0 should be low. So low, high, high, low. That should be a 6. I'm going to zoom out 2 steps. I zoomed in 2 steps. Now I'm going to zoom out 2 steps. Okay, so I can see more of it at once. Okay, so he said location 0, so I should be in location 0. And he said a 6, so I'm saying low, high, high, low. And let's turn it on, of course. We need power since it's memory. And I'm indicating location 0. I'm indicating a 6, but it's flip-flops, which I need to go walk through an edge. And that is this W. So I need to go back and forth in W. And there is my 6. I happen to be reading all the time. If I'm not reading, if I flip the R switch, I'm not reading and I see a 0. But if I'm have the R high, I am reading. So R is just level. If it's high, then I'm reading. But W is an edge. So let me change it to 7. So that would be low, high, high, high. So I would change 3. I'll look at your chat in a second. Oh, 0 should be a high. That's what I'm doing wrong. So that should be low, high, high, high. So that's a 7, but I haven't written 7. I've just prepared the 7. Let me put it in location 3. Being purposely difficult. So now I'm going to put a 7 in location 3, and I don't see it yet because, again, to write, I must go through an edge, back and forth. There's my 7 at location 3. Is key 0 the ones place? Okay. Good question. You see up here is my display. And in my display, this is the 8th place. Let me snip it so I can draw on it. In my display, this is the 8th place for to 1's place. And so these flip-flops feed the 1's place, and this switch feeds those and feed the 1's place. So this is the 1's place, and this is the 8's place. This is the address. This is the right. It needs to go through an edge. And so this is the data. All of this is data. Change my color. So these are the data. Specifically the 1's, 2's, 4's, and 8's place. This is the writing switch. Writing switches have to go through an edge. And now that says just add, and that looks silly. I don't know what happened before. It sounds like I want to add something, but add was for address. So A and B determine the address. The W was the right, but it needs to go through an edge. And 0, 1, 2, and 3 are the data, and the 0 is the 1's place, which we can tell by the way the display is. Any other questions? So you're ready to do this part of the lab. You just have to, I asked for different data at different addresses, I think. So you have to give me the other data at other addresses and write yourself some instructions. And anything else? So we've gone over the circuits you need to know. We've gone over the RAM circuit. We've gone over the LC. We've gone over the LR. The instructions, mapping out the instructions. You're going to ask me questions probably on Wednesday, I hope. I'm going to talk about LCs and oscillations for 10 minutes unless you ask me a question. Okay, you didn't ask me a question, so. All right, so here is this. First, the circuit was up, and that is an RC circuit, and then it charges the capacitor. And then I'm going to flip the switch down, and then the capacitor is connected to an inductor. That's what I'm going to talk about. So I just want to do word. I lost my word. I'm going to snip. And I'm going to have a capacitor connected to an inductor. I'll make it look a little bit more like a coil than the other picture. Okay. And maybe I'll give a ground. Okay. And the capacitor was charged with pluses on this side and minuses on that side when we started. Before it was connected to the inductor, it was connected to the resistor and the battery charged up the capacitor. Now these positive charges, they don't like each other, and the negative charges don't like each other, and they can't get together through this direct path because there's this dielectric material in there. But now there's a path through the inductor to the other side. So these charges start to leave to go through the inductor and get to the other side and meet up with the negatives that they're attracted to. Okay. But that is starting a current. So to discharge the capacitor, you need to start a current. You need to move some charges. Moving charges is a current. You're starting a current. And the inductor says, I'm against that. I don't like changing currents. I'm against that. Doesn't mean I prevent it entirely. It just means I'm going to slow you down. I'm not going to, you can't have any big abrupt changes. So the capacitor, in order to discharge, wants to start up a current, and the inductor is against that. Okay. But it doesn't stop the current from forming. It just kind of slows down the current from forming. Okay. So I'm going to try to erase my red without erasing my black if I can. So it doesn't stop it. It just sort of slows down the initialization. Okay. So now I get rid of some of my charges. I have a few charges left. And it's carrying on. There's now a current. So a current got going. The inductor was against it, but it got going. And now we have a few charges left, but they want to get out of there, so they try to get more current. And so now, as that carries on, then I am now, discharged. I finally got what I wanted, and the capacitor got what it wanted. It got discharged. To hell with it. Leave that one there. But to discharge, there it goes. Okay, but it set up a current. To do all that discharging, there was a current. Now the capacitor would like to stop. No, I'd like to stop. You'd like me to stop. You're the capacitor. You would like me to stop. But I'm an inductor, and you got me going with this current, and I say don't stop. Because I'm an inductor, and that's what I do. If I don't have a current and you try to start a current, I'm against you. And if you've started a current and you try to stop that current, I'm against you. I don't like change. That's what an inductor does. It does not let you change abruptly. So now the capacitor has gotten rid of all its charge. It would like to stop, but to discharge, it establishes current, and the inductor wants the current to keep going. And so there are charges here. They're just positive charges and neutral charges and negative charges, and they're neutral. But it starts to keep the positive charge going. It's breaking neutral things apart and leaving negatives behind. So now we're in this negative part of the cycle. So now the voltage across the capacitor is now negative because it's starting to charge the other way. And then it gets all charged up with positives on this side and negatives on that side. Now we're here, and it starts to discharge all in the opposite direction. And that's the oscillatory behavior, back and forth. It's either the capacitor has charge and wants to get rid of it, and then to get rid of it, it establishes a current. And then when the capacitor's happy, that's exactly when the inductor is not happy, because you're trying to change its current and it doesn't like change. So then it keeps the current coming and ends up charging the capacitor sort of in the opposite way than it was just charged. And that is the back and forth oscillatory behavior. It has what we call a natural frequency. So this takes place at a certain amount of time known as the natural frequency. And what you can do is bring in an outside frequency of your own, known as the driving frequency. I should talk more about this on. So if I just leave the inductor and the capacitor to itself, it has a frequency known as the natural frequency, but I can put in an AC circuit element, and that is the driver frequency. And now I have two frequencies. The driver wins. But when the natural frequency and the driver frequency are close to each other, then we get a phenomenon. So if the natural and the driver are close, we get something called resonance. I should talk about that on Wednesday, not rush it so much. But that's one of the important vocabulary words and sure to appear on the test. Okay, so now we're sort of out of time. So bring your questions on Wednesday. Somebody be ready to talk to me about instructions. I mean, somebody has to have tried it to say, you know, I thought step 4 was this, and then I'll say, no, not quite, I want blah. Or I can say, yes, that's right. But somebody's got to be willing to talk to me or chat with me. All right, I'm going to stop recording. I'm going to